Okay, so we are going to be deriving two equations, one for the temperature and one for the final pressure, with variation of altitude. We're going to be using this first equation, the basic equation of statics, first, and then we're going to be using this second equation, which is the internal energy relating the change in heat, or that small amount of heat added minus the pressure times specific volume, and then this is our ideal gas equation right here, and then this is our defining our heat capacity with pressure Cp, and this will be equal to 1 plus R over Cv, and we'll be seeing this in one of our equations, so this will help us out later. And then another thing I should mention is that we will have a constant, and this constant will end up being equal to Cp over Cv, and this is what we call a ratio of heat capacities. So we're going to go ahead and start, and we're going to start with using this equation, our basic equation of statics. So we can first say dP over dZ equals, and then we can change the density of the gas, which will be negative rho gz over times g, which is the acceleration. We can turn this into a separable equation and then integrate it to solve for relate the pressure and temperature. So we'll have dP over dZ, and then this will be equal to the density of the ideal gas will be this will be the mg over RT, and then when we can separate, so we will end up having dP. Oh, I actually forgot. This will also be times P right here. I forgot to add that in. So we'll have dP times P over T. Or sorry, we'll have dP times T over P, and then this will equal negative mg over RT, and then we can see, and then times dz. We'll also move the dz over here. So we can see that we can integrate this on both sides because it's a separable equation. Integrate by the altitude z and the pressure p. Oops. So we'll go ahead and do that, and we'll have from P1 to P2, we'll have T over P dP, and then this will be equal to negative mg over RT, or not T, sorry, because we moved the T over. So actually delete that T right there. We move the T over, so we'll just have a negative mg over R, and then we can integrate from Z1 to Z2, and then we'll have to say this is dz. And then this right here, that will be delta z. We're just going to call that delta z when we solve. But we're going to save this equation because we're going to want to find a specific temperature that we can plug into this in order to relate the pressure with the altitude. So next what we're going to want to do is use our second equation. When we use our second equation, the internal energy is equal to the small amount of heat, delta Q, minus the pressure times specific volume, dV. We can say that because it's adiabatic, that there's not going to be any heat transfer through the air pocket as it's moving up in altitude. So we can say that this is equal to 0. Excuse me. And then from the ideal gas, because it's reversible, we can say that since PV equals nRT, we can say that P is equal to RT over V. And since it's 1 mole of gas, we can ignore that end. We can kind of ignore that end because it's always just going to be multiplied by itself. So we're assuming that this is all in 1 mole of gas, remember. So this P we will change to the RT over V. So then we have our delta internal energy, delta U, du. Because it's adiabatic reversible, this depends on change in temperature. So we can say that this is Cv specific heat volume times the tangent temperature dt. And this will all be equal to negative RT over V times dV. So from looking at this equation, we know that we can kind of see, we can pull the Cv out, and we can integrate if we move this T over, and we can do a separable equation again. So we can do from T1 to T2, dt over t, since we move this t over, go to the denominator, and that will equal, we can pull this negative r out, so we'll have r, and then this will be times, and then we can integrate over here in terms of volume, v1 to v2, and then we'll have dv over v. And then if we keep solving this integration, we'll end up having cv, and then it's just an easy integration. We just have natural log. If we go and solve it all out, t2 over t1 equals negative r natural log v2 over v1. And our goal here is to try to get the temperature by itself. And we want to get temperature in terms of pressure. So we can change this volume once we isolate this CV and negative R and get rid of the natural logs. We can change this volume back to the pressure. But first we're going to move the CV over and use the log exponent rule. That we can move this in front of or we can move this terms in front to the exponent in order to get rid of the natural logs. So we'll end up having T2 over T1 equals V2 over V1. And this will be to the negative R over CV, since we move these specific heat over there to the other side. So for now, I'm just going to call this T2. We're just going to leave that as T1, and we'll leave the T1 as T to make things a little simpler. So we're going to just do T1 over T, and this will be, actually we'll leave T1 as it is. We'll just leave the T2 as T. We'll do T over T1, and this will be equal to, we can say the volume is equal to, RT over P. So we're going to change that. So we'll have RT over P and RT over P1. And we're going to do the same thing with the volumes that we did the temperature. So this V2, it's just V, and the V1 is just P. Or the V1 is just P1. And then this will be to the negative R over CV. So we can go ahead and scroll down, and we can keep solving. So we're going to have T over T1, and this will be equal to, the R's we're going to cancel, so we're going to end up having, oh, I forgot to put T1 down there. So we're going to end up having T over P times T1 over P1 to the negative R over CV. And then when we're moving down, we can just multiply the T over T1 on both sides. Oh, I actually think I might have wrote this wrong. So we're going to have T over T1 and then P over P1. That's what I actually meant to write. So we're going to move the T over T1 on both sides, the negative R over CV, and that is going to make it T over T1. And this will be 1 plus R over CV because we multiplied the T over T1 over, so that will be the 1 plus. And then we can get rid of this negative and switch the P over P1, and then we can make that P over P1, and this will be R over CV. So now looking at this from one of the terms we defined up here earlier, we know that the CP is equal to 1 plus R over CV. And then from that, we will also end up getting CP over CV, which will turn into our K, which is our specific heat capacity constant. So we know that our R over CV, we know that this will be equal to CP minus CV over CV. And then we know that this will be equal to CP over CV from what we defined earlier. And we said that CP over CV was K. So 1 plus that, so this CV minus, or CP minus CV over CV, this will have to equal 1, or K minus 1. So we can solve for that. So we are going to end up having T over T1 equals, to the K equals P over P1 to the K minus 1. And then if we want to just solve for T, temperature, which is what we want to do, we have T equals, and we are going to have T equals T1 times P over P1 to the K minus 1 over K. Okay, so this is our temperature equation that we're going to want to plug in to the equation that was relating the temperature and the pressure up here when we got it from the basic equation of statics. So we can take this equation that we circled up here and we can plug the T right into this equation. So what we're going to have is, I'll just go ahead and draw an arrow. We're going to have an integral of P1 to P2, T over P, dP, equals negative mg delta z over r. And then we have delta z because we had the integration from z1 to z2 of dz. And we said earlier that that was equal to delta z. So we're going to plug the t straight into this equation, and it's going to give us integral P1 to P2. T1 times P over P1 times K minus 1 over K equals negative mg delta z over r. And this will be all over P and then dP. So now looking at this, we can go ahead and we can try to take out the T1 and the P1. So and then move it over to this side of the equation to try to get the constants on one side and what we're actually solving on the other. So we have the integration of P1 to P2, the initial state of pressure, just the final state. And then we will have P to the K minus 1 over K minus 1. And then we'll say this, and then dP. And we'll say that this is equal to negative mg delta z over r. And then we can say times T1 P1. And we'll say this is times T1 times P1, and then this will be 1 minus K over K. So we can now solve this integration. And what we're going to get is we're going to have P2, and then we'll have K minus 1 over K, and then minus P1 K minus 1 over K. And then this is going to be all over K minus 1 over K. And then on this side, we have our mg delta z over r. And then times T1, because we moved the T1 over. And then this will be times P1 K minus 1 over K. So solving this, we'll have P2 K minus 1 over K minus P1 K minus 1 over K. And then we can multiply this K minus 1 over K on the other side. So we'll have P1 K minus 1 over K. I'm going to zoom out a little bit so it gives us a little bit more room. K minus 1 over K times negative mg delta z over r times T1 times K over K minus 1. And looking at this, we can see that we can actually factor out a P1. So we can factor out the P1 to the K minus 1 over K, and we can simplify this for P2. So we're going to end up having sorry, there's a little noise up there. We're going to end up having P2 to the K minus 1 over K equals, we're going to factor out the P1 and put it on the other side. So we're going to have P1 K minus 1 over K, and then we'll inside we're going to have 1 because we're going to factor in the P minus 1 over K, 1 minus K over K minus 1 times mg delta z over r times T1. And we're almost finished solving for our final pressure, in which relates the variation of altitude. So we're going to just isolate for P2 here, which is our final pressure, P2, and we're going to say this is equal to P1 times 1 minus K over K minus 1, the ratio of heat capacities, times mg delta Z over R times T1. And we can say this is raised to all to K over K minus 1. So this is our final pressure that relates the change in altitude. As you can see that the changing in this equation is the delta Z, which is the change in altitude. And the only other steps we need to do next is plug this into the temperature equation and solve for that. So we can plug this pressure straight into this temperature equation we used up here. So we're going to plug that into over there. So we have T equals T1. Sorry, my handwriting is pretty bad. T equals T1 times P over P1, 1 minus K over K, or K minus 1 over K. K minus 1 over K. So now we're just going to plug this pressure into this pressure right here. We're going to plug this pressure into this pressure right there, and we're going to do some cancellations and hopefully solve for this final temperature as well. So we'll just say our T, and we'll call this final temperature T2. We'll say T2 is equal to T1 times P1 times 1 minus K over K minus 1. Messed up there. K over K minus 1 times mg delta Z over R times T1. And this will be to K over K minus 1. And then we'll do all this over P1. And then this will all be raised to the K minus 1 over K. So looking at this equation, we can see that these P1s will cancel, and the constants of the heat capacities will also cancel. So that our final temperature will end up being T2 equals T1 times 1 minus K over K minus 1 times mg delta Z, change in altitude, over RT 1. And this will be our equation for final temperature, the variation of altitude. As you can see, the change in this equation is our delta Z, and again, this is our altitude. So we have now solved for a temperature and pressure that relates, that uses the basic equation of statics and the internal energy concepts to relate temperature and pressure with change in altitude. Thank you for watching, and have a good day.